First, if we take a look at the Arduino board, we can see that, as we observed last time, there are digital pins on the top and analog input pins on the bottom. First, we will check the analog input signals. If you look at the bottom right here, it says analog in and lists A0, A1 up to A5. You can choose any of these pins to use for analog input. Let's try checking the analog input on the Arduino. First of all, for analog inputs, there is no need to set the pin mode for direction like we did when controlling digital pins last time. You can directly read the analog input. I will read a UINT16 value, and for reference, I will check A0. So let's define the pin as ADC, just ADC A0. For your information, A0 is designated as a pin number in the Arduino using a macro. When you read this with an empty ADC, the value will be read between 0 and 1023. This value represents a 10-bit reading. However, as I explained last time, and the time before, other boards besides the UNO support resolutions up to 12 bits. If you have a board, as I explained before, you can change the analog resolution to 12 bits for reading. With 12 bits, that means it can read up to 4096. So it will read from 0 to 4095. However, just for reference, since this also receives input, you need to utilize pull-up or pull-down on the input pins when connecting other analog devices such as a potentiometer or analog-related sensors. If you read without any connections, it will be in a floating state, which means random values will come in. In this case, there are instances where this floating state is intentionally used to obtain values, particularly when using the random function in Arduino, as it initializes the random seed for generating random numbers. For example, this floating state can be quite useful in certain scenarios. There is a random seed function, and when typically calling this random seed, the analog read values are usually often used. If this happens, I'll completely eliminate the equations like this. When I read the analog value in a floating state, for instance, I don't know what kind of transition value will come in. You never know what random value will come in between 0 and 1023. We use that randomness to initialize the generation of random numbers arbitrarily. So after that, you call the random function wherever you want to generate and use random numbers. In some cases, this is done intentionally by using a floating state, but if you are using a real sensor or potentiometer, you would need to connect a pull-down or pull-up resistor to that input pin. In this state, let's assume that instead of analog input, we are trying an analog output. Now, if you take another look at the Arduino board, you will see digital pins numbered from 0 to 13, and there are some with a wavy symbol next to them. This means that the wave pattern can be output as PWM analog output. So here you can see that pins 3, 5, 6, 9, 10, and 11 can be used for analog output. In this case, I will randomly choose pin 9. Then let's simply, clearly, and concisely define the PWM as 9. Here, I will set pin mode PWM.output to initialize the output to be off at first to provide a clear understanding of the process and ensure that the output is correctly initialized. And then I will proceed like this before moving on to the next steps. Let's assume that the LED is connected and that, such as a potentiometer, is connected to the analog input. Then, if we say that the brightness of the LED is dim when the value coming from the potentiometer is small, and bright when the value is large. The function that is commonly used for this, in general, is the map function, which is typically used in this context. We talked about brightness mapping, and we mentioned that the ADC value we receive as an analog input ranges from 0 to 1023. This value is stored in value, and since it ranges from 0 to 1023, it is too large to be stored in 8 bits. So we are at the present time using 16 bits. In this state, the value falls within the ADC range of 0 to 1023. So initially, we have 0 to 1023, and then I convert it to 0 to 255, and then use it for analog output. For example, in the case of analog write, the value that can be set when adjusting the voltage analogically is fundamentally from 0 to 255. It's exactly 8 bits. So here, the analog input value that we read is currently between 0 and 1023, but we convert it to a range of 0 to 255. Then the converted value goes into brightness, and brightness is set to control the voltage of the PWM value on that pin through analog write. We can control the analog output like this with a delay of 100, just as we could change the resolution of the analog input when performing an analog read. Similarly, there are boards that allow you to change the resolution for controlling analog PWM, which can be more than just the simple 8-bit. Some boards can switch to 10-bit or 12-bit. Similarly, at that time, after changing the resolution of the analog write, you can set it to the desired resolution. Now, you can control the analog input and output like this. In this session, we worked on controlling the analog input and output of the Arduino. In the next session, we will cover serial communication, which is commonly used for communication between the Arduino and PC. I'll see you next